We're going to be looking at fluid pressure right now and going over what a fluid is. We're going to be looking at the English units and the metric units of this. And we're going to come up to a number that might look very familiar to chemistry when we were looking at pressure. And then we'll talk very briefly about something called Pascal's principle. And Pascal is a scientist whose the unit is named after for pressure. So let's take a look at the definition of fluid. When people think of fluid, they usually think of something like water. They usually think of something that is a liquid. But here's the definition of a fluid. So a fluid is something that flows, like water, and has no shape, like water. However, there actually is an additional phase that meets this definition of a fluid, that flows and has no shape. If you can imagine Chicago, the windy city, it's called such because of the winds that come into the city. However, the winds are channeled like they were water through the skyscrapers. And as they squeeze between the skyscrapers, they actually increase their velocity. So gases actually, when people are studying gases, they will often study how it is very, very fluid because it also flows and has no shape. So fluids are both liquids and gases. We're first going to take a look at the English system of how the units are presented to us. So if you think of the English system, how do you measure your tire pressure? It's measured in pounds per square inch, or PSI. And we're going to be doing some conversions from PSI to the metric version as well. So PSI, again, the units for this is going to be pounds per inch squared, or square inch. Pounds for the P, square for the S, I for the inch. And if you look at this, this is going to be a similar formula from chemistry. Measuring pressure. Pressure is equal to, it's the force, which is the weight pushing down, the weight force, and inches squared, length times width, gives us area. So here's the kind of the master formula for this. However, we don't measure things in pounds per square inch. In the metric system, they're measured in, well, force is going to be measured in newtons. Area, instead of inches squared, you're going to have meters squared. And the units for newtons over meters squared is called a Pascal. You have 1 Pascal, or 1 PA. And this is the scientist Pascal, who we will discuss in just a little bit. So we're going to first start with the atmospheric pressure. This is just the pressure of all the molecules of oxygen and nitrogen that are pushing down on us right now. So we have atmospheric pressure, and that comes out to be about 10 newtons per centimeter squared, meaning 10 newtons of force is pushing down on you right now every square centimeter. But what I'd like to do is to convert this into the meter squared, and just to get some practice doing this because we're going to be doing this a few times during our labs. So 10 newtons over centimeter squared. We want to convert this not from in centimeters squared, but we want to get it to meters squared. We already have the newtons. So what we're going to do is we're going to have a unit converter, and we're going to convert the centimeters into meters. 1 meter is equal to 100 centimeters. I'm doing this twice because we have centimeters squared, so we need centimeters squared to be canceled on the top. So the squared is down here, would cancel with 2 of the centimeters, so we have to have the same thing. Centimeters over meters. So again, the centimeters squared cancels with those centimeters squareds. And now I'm left with 100,000 newtons per meter squared. Well, using our new unit of pascals, a Newton per meter squared is going to be 100,000 pascals. But with large pressures such as this, they're usually not given in pascals, they're given in kilopascals, and so we have 100 kilopascals or kilopascals. This might look a little bit familiar because atmospheric pressure of 10 newtons per square centimeter is equal to 101.3 kilopascals, which you might remember from chemistry. So here's just a very quick demonstration to demonstrate Pascal's principle. So this is a syringe. It's filled with glue. It's a very, very thick and viscous fluid. And I'm going to press on one end, and something magical is going to happen. Not that sound. So hopefully, can you see that? You can. I'm pushing on one end, and magically, the glue is coming out the other side. How does that happen? That happens because of Pascal's principle. So if you can imagine the same principle, and we're going to discuss a tube of toothpaste. Okay, quick question for you. Do you squeeze the toothpaste from the middle, or do you squeeze it from the end? Well, some people can debate about this, and some people in marriages can fight about this, but it comes out the same regardless of whether you squeeze it from the middle or you squeeze it from the end, so it really doesn't matter. That's my opinion. So imagine this is a tube of toothpaste, okay, and so it narrows down to this nozzle right here, and it comes out right here. So inside your toothpaste, this is your fluid. And let's say you do apply some pressure on this end over here, because we were applying the pressure on this syringe from one end as well. So we're going to apply the pressure. I squeeze it from the middle. My wife squeezes it from the end. So that's with that discussion a little bit earlier. But again, it doesn't really matter because it all comes out the same way anyway. We now have our separate toothpastes, and it's no longer a problem. So we apply pressure on this end, and what happens is we get motion coming out from this end. So if you think of all these particles, I'm going to draw them. It's going to look like a solid, so I'm going to try to draw them a little bit more randomly and non-crystalline like this. When you apply a force to this particle right here, that force then gets transmitted to this particle, which gets transmitted to this particle, and this particle, etc. So the force gets transmitted to the neighboring particles. And this is what is known as Pascal's principle. Pascal's principle indicates that when pressure is applied at one point, I'm just going to abbreviate pressure. When pressure is applied at one point, it is equally transmitted through the fluid. It's equally transmitted through the fluid. Pascal's principle: when pressure is applied at one point, it is equally transmitted through the fluid. This is going to be very important to remember and to recall when we go into the next section, and that's going to be taking a look at hydraulic pressure. So now what I'd like you to do is get some practice in converting from pounds per square inch to newtons per meter squared or pascals. We're going to calculate your foot pressure. So please go to the next video, which looks at calculating your foot pressure.